So this is my review of kinematics. Kinematics is all about motion, and it's really based on three concepts: displacement, velocity, and acceleration. And then we have our kinematics formulas. I'm not going to write all of them, but the two that you need to know and that get used the most: 1/2 at squared, d equals 1/2 at squared plus vit, and vf squared equals vi squared plus 2ad. And then there's free fall. Usually we're talking about on the surface of the earth. And then there's projectile motion. Three types of projectile motion. You can shoot something into the air, you can shoot it on an angle, or you can roll it off of a table. And so let's just go through each of these really quick, and then we're going to talk about kinematics graphing, and that's really all there is to know. So displacement, right? That's this. We write it. These are all vectors, and displacement is that arrow that represents the shortest path between two positions. So whatever these may be, I'm going to call them A and B. Could be home and school or anything. There's the actual distance traveled, which maybe is this curvy path that looks like this. But then we have the displacement from A to B is going to be a vector that starts at A and ultimately ends up at B. Maybe I label that R is my displacement vector, or maybe instead I call that D for displacement. And now velocity is just the change in displacement with respect to time. So my velocity vector is just a change in displacement with respect to time. And then acceleration, change in velocity with respect to time. So this is where we get that v is equal to d over t formula. It only works if there's no acceleration. And here, a is v over t, and this is where we get the vf equals vi plus at formula from. In the situation of free fall, if I'm just dropping an object, let's say I have some mass here, and he starts out with vi that's equal to 0, right? As he falls, this distance is going to end up getting greater and greater because he's accelerating as he's falling. And then this would be the vf down here at the bottom. And that acceleration is little g, and that's negative 9.8 meters per second squared. And then, of course, the distance that he falls is going to be equal to the height. And usually we write that as a negative distance. And so if I want to find out how long it takes to fall, I'm going to use this. I can use this formula here, and that's going to end up giving me the time. If I want to know how fast it's going at the bottom, and I don't have the time yet, then I can use this formula here, and it's going to show me how fast it's going at the bottom. Now, one of these turned into a star, and the other one didn't. But so now we have projectile motion, right? So the easiest type of projectile motion is similar to free fall, as if I were to just launch this thing up in the air. So if I launch this straight up into the air, it's going to reach the top. It's going to come back down again. When it's at the same level, then this VF is going to have the same magnitude as VI, just that it's going to be in the negative direction. And then up here, at this point, this V top, we'll call it, V top is going to be equal to 0. And so if you use VI and V top, that's half the trip. So if you want to find the height, you're going to use half the trip. And if we're talking about the entire trip, then we can use VI and then VF. Because if we know VI, VF is going to be the same value, just negative. And so then with projectile motion, we really have two types of projectile motion. Well, we have, in addition to what we already have here. So two-dimensional projectile motion, I can now take some object and I can launch it up on an angle like this. So when I launch it up on an angle, it ends up having this trajectory and comes back down here at the bottom. And the same thing is true, that this VF here, that's going to be equal to negative the VI value. And when I have projectile motion here and it's launched at some angle, the velocity in the x isn't changing. And how do we get that velocity in the x? Well, the trig is that v in the x is equal to v times cosine theta, and that's going to be true everywhere. That's going to be the same down here. That vx is going to be exactly the same here, even at the top. My v top is going to be equal to vx because at the top, vy at that instant is going to be equal to 0. And the way we find vy is v times sine of the angle. And that's changing, right? Vy is getting less, 0, and then it's getting greater, greater in the negative direction here. And then the other type of projectile motion that we need to be aware of is horizontal projectile motion. And that's where the object comes off with some speed. And that vi, that's really going to be equal to the velocity in the x. And vi in the y, well, that's going to be 0 because he's only moving in the x direction. And his trajectory is going to look like this. And this is putting a target here to remind us this is like shoot for your grade. So in this situation, again, Vx is going to remain constant for the entire time. And so let's look at some other things here. How far away this guy lands from the table, that's going to be his dx, right? And there's no acceleration in the x direction, so dx is always going to be Vx times the time. And how do we get the time? Well, sometimes if they give us dx, we might be working backwards, but usually we're going to use the table height. That's our dy, and we're going to use that 1/2 at squared to get us the time that it takes. Over here in this example, our distance in the x is this distance here. And again, the distance in the x is going to be equal to the velocity, just the x component, times the time. Now for the entire trip, the distance in the y is going to be 0 because he starts on the ground and he ends up on the ground. But for half the trip, if we do half the trip, then this height is equal to the distance in the y, right? And so here I might have time 1/2, and here I have time 1/2. So if I'm finding how high it went, even in the other example that we did, then I'm going to take half the trip to figure that out. So let's transition over here to this document and talk a little bit about kinematics graphing. So if something's going at constant, so there's three graphs, right? We want to talk about position or displacement or distance versus time, and then velocity or speed versus time, and then acceleration versus time. And if something's going at a constant speed, right, it may or may not start from rest, may or may not start at the origin, but if it's going at a constant speed, we're going to have a straight line here. This point here, this is the y-intercept. That's like the initial position that it starts at. And this slope, the slope of this is going to be equal to his velocity. So positive slope, positive velocity. So over here, I'm going to have a flat line because the velocity is constant. And if the velocity is constant, then my acceleration is going to be equal to 0. And this area under the curve of velocity versus time, that area is equal to the displacement. If I have an object that's speeding up, well, I think it's easier to do the acceleration first. If I have an object that's speeding up, it's going to have a positive acceleration. So velocity versus time has to have a positive slope. So maybe if it starts from rest, I draw it from the origin. But if it doesn't start from rest, if it starts from here, I might get this line where this slope equals the acceleration. This point would be the initial velocity, and then this point over here, that would be the final velocity. And again, this area all the way down to the x-axis, that area would be equal to the displacement. And by the way, how would you take the area if it's this strange shape? Well, it's a little bit advanced, but if you had to do it, you would take the area of that square, which would be length times width, and then you would take the area of this triangle, which should be 1/2 base times height. And those two areas added together would be the displacement of the object. So now let's look at position versus time. If the object's speeding up, that's going to be an upward curve like this. And how do I know it's going to be an upward curve? Well, the slope has to be increasing. So here the slope is relatively mellow. Here the slope is steeper. Here the slope is steeper. Here the slope is super steep. So this is something that's speeding up. So now let's look at something that's slowing down. We can go a little faster, but it's going to be a negative acceleration versus time. This is going to have a negative slope, where this is going to be VI, and then this down here would be VF. It's velocity versus time. Let's draw him from the origin, going very fast, and then he's going to slow down. And when this becomes horizontal, that would be the point at which this reaches 0. And again, we can look at the slope here. Here he's going very fast, slower, slower, and then up here he's going 0. And so let's look at the last situation here. Projectile motion in the y direction. So if we transition to the bottom here, distance versus time, velocity versus time, acceleration versus time. And we're going to talk about projectile motion in the y direction. So this is either an object that's being shot straight up, or maybe it's being shot at an angle, but we're only looking at the y component of the velocity. And again, it's easiest to do the acceleration first. So with the acceleration, it's going to be a straight line because the acceleration is equal to negative 9.8 meters per second squared. And the velocity, right, starts out being fast. At the top, the velocity is going to be 0, and then the velocity is going to be negative. And remember, when it falls to the ground, it's going to have a VF that's equal to negative VI. So maybe I go up 2, here's my VI, and then 1, 2, 3, 4, I go over 4. This is the highest point, and then 1, 2, 3, 4, and down here, that's going to be my VF down here. And so this is going to be a straight line, and my slope is going to be equal to negative 9.8 meters per second squared. And this positive area here is going to be how high the object goes, and then that would be equal in magnitude to the negative area here because it comes back to the ground again. So here this guy starts on the ground at 1, 2, 3, 4. He's at his highest point, and then 5, 6, 7, 8. He's back to the ground again. He starts out like this because he's going fast. Slope becomes 0 at the top, and then he comes back down again. So if I were to show the slope, he has a very steep positive slope. Here he's slowing down. At the top he's 0. He's speeding up in the negative direction, and now he's going very fast in the negative. So that's just a quick overview of the major topics in kinematics.